I started the recording. Yes.
Okay. So good afternoon, everyone. It's a pleasure to be here and to give this talk in front of such an audience. And I'll be talking mostly about matching estimators in causal inference. And I think most of you know what is meant by causality. Whenever we say the term causality, I think there is one single statement which stands out, that is correlation does not imply causation. And I think many of you have seen this simple joke from xkcd.com. And unfortunately, most of the classical textbooks on statistics, they do not talk about causality that much, or even if they talk, they just mention this statement only, I should say. But in practice, it is the question of causality that is many practitioners, they actually want to ask in real life situations. Okay. And one thing that I should have mentioned earlier, that please feel free to stop me anywhere in the talk, because I am learning this subject for the first time. So questions, any kind of questions will be helpful. Okay. So let's start with some basic examples. I think in everyday life, we say some statements which are essentially questions about causality, such as, did my headache go away because I took aspirin? Or say, does smoking cause lung cancer? And many such questions that people ask in everyday life. But how to formalize it? So our approach here will be through something called potential outcomes, and we'll be mentioning what is that. And this approach was first, I think, proposed by Neyman in his master's thesis, and later it was extended broadly by Donald Rubin, I think in the 70s. Okay, so so what are potential outcomes? We have some units. For example, in the aspirin example, I myself at a particular point of time can be a unit. And by action, we mean I may or may not take the aspirin. So I'm contemplating whether or not to take the aspirin, and my taking aspirin or not taking aspirin, that is the action. And to each action unit pair, we associate a potential outcome. Okay. For example, we may denote by Y aspirin the potential outcome that indicates whether my headache is gone after, say, half an hour after I take aspirin. And similarly, if I do not take aspirin, then the potential outcome may be denoted by Y no aspirin. And this outcome can be binary, can be taken on a scale, whatever. And the causal effect of aspirin on headache, that is basically the comparison between these two potential outcomes. Okay. Now, there is a problem which you might have guessed already. That is, we cannot see both the potential outcomes in a single experiment, because the causal effect is because I might take aspirin today and I might not take aspirin tomorrow, but I myself at this point of time and tomorrow, they are considered as different units. And the causal effect involves the comparison of different potential outcomes for the same unit at the same point of time in post-treatment. Okay, so since at most one of the potential outcomes is observed, we never know how to compare the difference in potential outcomes for the same unit. Okay. So I think there is a movie called It's a Wonderful Life, where there is a character named George. He says that he becomes very depressed and says that the world would have been a better place had I not been ever born. Now, the problem with this statement is that we never know how the world would have been had George never born. But it's a movie, so there an angel appears and she shows George how the world would have been had he not been born. And obviously there are some consequences, like George's son will never be born because George is not born in that world that is called the counterfactual world. And there are also some very bizarre consequences. For example, in the real world, George's brother, he becomes a World War II hero. But in the counterfactual worlds, George's brother dies at a tender age because George was not there to save him. Now, in the movie, George gets to see both the two worlds, counterfactual world and real world, but we don't have the opportunity. So what should we do? This is called the fundamental problem of causal inference, that we do not observe all the potential outcomes. So the way out is that there is a very simple way out. We need to consider multiple units. That is, some units are given one treatment and some units are given other treatment. Say some units are given aspirin, some units are not given aspirin, and then we have to compare. But just considering multiple units is not enough. We need some assumptions. For example, let's take the aspirin example once again, you and I, and there are two possible treatments, aspirin or no aspirin. Now, we may assume that the two aspirin tablets are equally effective. That is a very modest assumption. And we might assume that whether you take an aspirin, that does not affect my headache, whether my headache is gone or not, and vice versa. These are two assumptions that we are making. And note that these two are very modest kind of assumptions, and we in this example they should hold. But we have to keep in mind that these are just assumptions and cannot be verified. For example, okay, can you think of any situation where such assumptions may fail? The first one is easy, I think, because the two aspirin tablets can be of different brands, or to take the more worst case is that one of the aspirin tablets is expired. Then the first assumption is not holds there. And okay, now can you tell any scenario where the second assumption is failed?
So passive smoking can be an example.
Yes, passive smoking can be an example. And the example I had in mind is in a recent context is that suppose you consider the immunization against COVID-19, and your immunization, suppose you take a vaccine, then if nobody around you takes the vaccine, then your immunization can be as effective as not taking any vaccine, right? And conversely, if everyone around you takes a good vaccine, then your immunization becomes superfluous. So that is an example where this assumption is violated. So in such cases, there are way outs. For example, we can consider a community as a whole community as a single unit. Suppose all the students in the ISI campus as a single unit. So so there are way outs, but these two assumptions, they are very crucial, and they are called the stable unit treatment value assumptions, or the sadhva assumption. Not, I should not say sadhva assumption, because A is for assumption. So this is called sadhva. And more generally, they state that across units, there are no different forms for each treatment level, and the potential outcomes for any unit, they do not interfere with each other. Okay. And this sadhva assumption is very crucial, and it is always assumed in works in causal inference. And assuming this, we may introduce now the notation, say yi equal to yi wi, where wi is an indicator of the treatment given to the ith unit, because you see the potential outcome of the ith unit will be now a function of the treatment given to the ith unit only. Okay, otherwise it would have been dependent on other units. So we have this notation yi equal to yi wi, and for simplicity, we'll assume that there are only two levels of treatment: active treatment and no treatment or control. So w equal to 1 and w equal to 0. Okay. Okay. So now next, the question is, what do we want to estimate? So we have multiple units, and we have introduced the notation yi equal to yi wi. Then what do we want to estimate? Now, for the ith unit, we might define the causal effect as simply yi1 minus yi0. Okay. So this is the potential outcome had the ith treatment taken the active, had the ith unit taken the active treatment, and this is the potential outcome had the ith unit not taken the treatment. And as you might have noted that we never observed this delta i's, right? So we assume that so we have nothing to do if delta i's are different for different. Of course, delta i's will be different, but we have to assume that on an average they are same, so their expectation is same, and we estimate this quantity, which is called the average treatment effect. So this is we assume that this is same for all the units. And similarly, there is another estimate, which is the average treatment effect on the treated. So that is done by simply conditioning on w equal to 1. So here we, I think here is a typo. This should be wi equal to 1. So we are basically assuming that the ith treatment has been exposed to the active treatment, and for that unit, ith unit, we are finding what is the effect of the treatment. Okay, so these two, they are the main quantities that we want to estimate here, and these quantities also appear in the context of randomized control, randomized settings. So in randomized clinical trials, what do? We take there are n units, and we randomly assign them into two groups, treatment groups and control groups. So here are two assumptions that we are making. First one is, of course, sadhava, and the second one is the random treatment assignment. That is, wi will be independent of, this is the notation for independence. So wi will be independent of yi0 and yi1. And we may assume that among the n units, there are n1 many who are treated and n not many who form the control group. So in this setting, what should be an estimator of this quantity? There is a very reasonable estimator, which is what? Simply the difference in the averages, right? The average outcome of the treatment group and the average outcome of the control group. And that estimator is called the difference in mean estimator for obvious reason. And since the assignment of these wi's are done by done at random, so the standard methods apply here very easily. For example, what are the properties of this estimator? First of all, it is simple to calculate, and you can see that it is unbiased, and you can easily establish that it is also consistent. And there are other properties. For example, an asymptotic normality can also be shown by multiplying it with square root of n maybe. And we can construct confidence intervals using simply some simple plug-in estimators we can construct. So the theory is very clear in this particular setup. And this is the setup of randomized clinical trials. But in most of the cases when we ask causal questions, we do not have a randomized clinical trial. We have an observational setup. So what is that? For example, suppose we ask the question that, does smoking cause lung cancer? And then can we form a randomized control trial in this case? Can we just randomly select one person and say you have to start smoking from now because you are in the control group, sorry, you are in the treatment group, and you pick one smoker, and you say that you are in the control group, so you cannot smoke any further? That is meaningless, right? So doing a randomized trial is sort of unethical here. And there can be, I can give another example. Say we want to find what is the effect of seatbelts on severity of accidents. Then we cannot just randomly assign people to seatbelt and no seatbelt groups. That would be simply unethical. And in this example, can we answer this question by only estimating these two quantities, probabilities of lung cancer given smoker and probabilities of lung cancer given non-smoker? No, right? Why? Because people already have formed the smoker and non-smoker group, so there can be confounding effects. Okay. For example, in the other example that I just told you, that we want to find whether seatbelts have an effect in severity of accidents. It might happen that people who are running at a higher speed, they tend to wear seatbelts, but people who are not going very fast, they do not wear seatbelts. But there can be accidents in both the cases. So there can be confounding factors, and for that we cannot simply answer it using this type of quantities. And now comes the question: does the difference in means estimator work in such frameworks? What do you think? We are considering the difference of the responses of the two groups. Would it work in this observational framework? It should not, right? For the same reason. So here is an example. So suppose we have Joey, who's suffering from some disease, and for him it is more severe. So he is given an active treatment, whereas for Phoebe the pain is less severe. So Phoebe is in the control group. Now here can be confounding effects if you consider difference in means. If you just consider the difference in their responses, there can be many confounding effects. For example, gender is one thing, and severity of pain is another effect. So, and there can be other physical characteristics, right? So the difference in the simple estimator that we just told for randomized control trials, the difference in mean estimator, that suffers from bias due to specific variables. And this is where matching enters. So matching was, I think, introduced by Donald Rubin, I think. And he also introduced it in the same context, that we want to remove bias due to specific variables. So what is matching? The key idea is that for each unit, we find one or more units, they have similar features, but receiving the opposite treatment. And then we just consider their difference. That's difference in the responses. So for Joey, we do something like this. We find another person who has similar characteristics with Joey. And similarly for Phoebe also we do. And that person should be receiving the opposite treatment level. Otherwise, it is meaningless. Okay. So this is the key idea of matching. And now you may ask how matching is done. Of course, this is just a funny example. In real life, what we do, we have some set of covariate values, right? Along with any, whenever a patient goes, we collect some covariate values, and on the basis of those covariate values, we select. Of course, the doctor decides whether or not to give treatment or not. But on the same covariate, using the same covariate values, we can do matching. For example, we can do nearest neighbor matching. How? Assume that for each unit, we observe the triplet Y, X, and W, where Y is, of course, the recorded outcome, and W is the treatment indicator, and X is the set of covariate values, some measurements on the patient. And now we are given Yi, Xi, Wi for I equal to 1 to n. And then we can define this JMI, J sub mi. What is that? That is simply the index J of the unit in the opposite treatment group, which is the mth closest one in terms of the characteristics. So mathematically, we define like this. We consider this set. Note that we are taking Wk equal to 1 minus Wi, so that the kth unit is in the other treatment group. And what does this say? This says that the jth observation, or the jth unit, is the mth closest one in terms of some distance. We can consider the Euclidean distance, for example. Okay. And we fix a m, and we consider this set. This set consists of the units in the other treatment group, which are m many units in the other treatment group, which are the closest to the ith unit in terms of the x characteristics. So is the concept clear? You can ask any questions if you have at this moment. And of course, using the Euclidean distance is not necessary. You can use any kind of distance. And of course, you should have questions now, because there are many issues. For example, there can be ties. So what to do if we have ties? Now, usually what is done is that either we assume that the covariates, at least one of the covariates is continuous, so that there are no ties with probability 1, or if all the covariates are discrete, then that is completely another regime where we can apply different methods. And usually what is done is something called propensity scores, and using propensity scores, the matching is done in such situations. Okay. So just keep this notation in mind that JMI denotes the units that the M units that are in the other treatment group, which are closest to the ith observation in terms of characteristics. Okay. So now we have another very important assumption, and that directly motivated from the randomized control trials. Oh, sorry, it should be randomized clinical trials. Okay, so in randomized clinical trials, we have this independence. We know that y1 and y0, they are independent. Up to potential outcomes, they are independent of the indicators, the treatment indicator. But here we cannot assume, because this is an observational setup. So here what we assume is that if we condition on the covariate values, then we have independence, then we have this independence. Okay. So this is known as the unconfoundedness assumption. And there are other names. I think some people call it exogeneity, or I think it was first articulated in this form by Rosenbaum and Rubin, and I think they called it something else. I cannot remember. I think some stability or something else. Okay. So, but anyway, so this assumption is usually posed in papers on matching, because without it we cannot meaningfully estimate what we want to estimate. So for example, let's see what does it imply. So we have y1 and y0, they are independent of w, condition on x. So from that conditional independence, we can write this line, right? The expectation of y1 given x, that is same as the expectation of y1 given w equal to 1 and x. Because conditioned upon x, y1 is independent of w. And now you take another expectation with respect to x, and you get this. And then this can be written as simply this by the Tower property of expectation. And we can also write this as this, because remember the notation we used in the beginning, yi equal to yiw. So if we fix that w equal to 1, that means this person is being given the active treatment, and so y1 should be same as the recorded outcome y. I mean the recorded outcome is same as y1, the potential outcome y1. And similarly, we can replace these ones by zeros and get this relation, and then just subtract one of it from the another, and recall that this tau was the expectation of y1 minus y0, and we can just write it as this, conditioned upon x, and then use the above two relations to write it like this. So this expression is just derived from the unconfoundedness assumption, and this will actually motivate us that how we want to estimate it, estimate tau in this setup. So basically what we have to do, when an observation is being given the active treatment, we know what is y is y1. But when it is not given the treatment, the active treatment, we have to somehow impute the value y1, right? And similarly for w equal to 0. So we basically impute the potential outcome using the idea of matching. So note that if w equal to 0, that means the ith unit is in the control group, and then we do not have to impute anything. We directly have this observation. But when it is in the other group, then we impute it using the response of the units which are closest to it, and that is simply this average. Simple enough. Similarly, for yi1, we can impute like this, and then simply consider the difference, the difference in the averages like this. Sorry, the average of the differences. So this is the matching estimator for average treatment effect. And note that we do not directly have independence here. It is dependent through the covariate values, but still we have something to proceed. Okay, so this was for average treatment effect tau. Next, we have to do it for average treatment effect on the treated, which is tau upper I think superscript t. And but whatever we did for tau, we can simply mimic this for this also, ATET. So we just condition upon x and then use the unconfoundedness assumption, and we get something like this. And note that here we want to estimate the average treatment effect on the treated. So how will you estimate this quantity? We can estimate this quantity by taking the average in the response values for the treatment group. And now look at this, the second quantity. How will you estimate this quantity? So the matching estimator for this is written as this. This is directly from what we did for tau, but we can equivalently write it as this. And this is what I was talking about earlier, that you just separate it out. The first quantity is a very intuitive estimator of this quantity, right? And the second thing, what is the second thing? 1 by n1, this summation, and then 1 by n, this summation. Note that the inner average, this average is estimating this quantity, right? And then we are doing this in order to get the whole thing. So this is really intuitive, and these are the two estimators that we will talk about in the second part of the talk. We'll consider the large sample properties of these two estimators. One is this, and the other one is this one. Okay. So any questions till now? Should I proceed? Okay, let me proceed. Okay, two remarks. One thing is that here we are considering a fixed m. Okay, we are assuming that m is fixed, and then we are doing the matching. Now there are other approaches. For example, Heckman, Ichimura, and Todd, they proposed estimators that treat the number of matches as increasing function of the sample size. And how did they do? Actually, note that the key estimation that we are doing is this imputation. So instead of doing this imputation, they proceed in a different manner. They did a kernel-based estimation for this, kernel-based imputation for this. Okay, but here we will consider the constant m case only. And there is another issue that I didn't talk about in the earlier slides. That is that the nearest neighbor matching can be done both with or without replacement, right? When we are doing matching for each unit, we are selecting some m many from the other pool. We can do this both with or without replacement. And it turns out that the theory for with or without replacement, they are much different. Okay. For example, in case of with replacement, we have some sort of independence, right? But when you consider without replacement, okay, first of all, how to do without replacement? We cannot just take arbitrarily, right? You have to sort of be optimal in some way. So what do? We do without replacement in a way such that this quantity is minimized. Note that this quantity is simply it is basically the, what should I say, the intercluster distances. So for each unit here, I am taking the distance of it through its to its neighbors in the other pool and just summing it up. So this is called the sum of discrepancies, and matching without replacement should be done in order to in a way that this is minimized. Now, of course, this is a optimization problem, and that is a whole another issue how to do it. And in fact, I have not seen any implementation of this thing. Usually what is done in practice is that people do not go for M matching. They just take M equal to 1, just the nearest neighbor. For nearest neighbor matching, with M equal to 1, with or without replacement, they are the same. Okay. So just a few more notations. So this for each treatment I, Kni denotes the number of times the ith unit will be used as a match, will be used in the matching. Okay. So for each unit, it can be used multiple times, right? It can be closest to some other units in the other pool multiple times. In case of matching without replacement, Kni will be 0 or 1. But in case of with replacement, this can be as large as the whole, the size of the other group. And we denote the mean function and the variance, of course, conditional upon W. Oh, okay. This here is another typo. Here should be conditioned upon W also. I mean this should also be here. Okay. So these are just mean functions and the variance. Okay. Now let us come to the large sample properties. So we'll be discussing a special decomposition for tau hat. Let us first do it for tau hat, and then we do it for tau hat power t. So the decomposition is something like this. Of course, we have to discuss what are the components. So the first component is something like this, which is not dependent on the yi's. It is simply a function of the xi's, the covariate values. And the second, I think I forgot its name. This has some name. Okay. And the second component is slightly bigger. It looks bigger. And note that it is concerned about the residuals. And the last component, we can actually show that these first two components, they are unbiased. So whatever bias we have in tau hat, that comes solely from Bn. So this Bn, this is called the conditional bias, and if you take expectation of it, it is the unconditional bias. Okay. So these are just some expressions, and note that Kni appears here. In fact, Kni, I think, will be very important in the variances. A large Kni may make the variance large or something like that. Okay. So as I said, this is the conditional bias, and the first two terms are actually well behaved. They have zero mean, and they are found to be of order into the power minus half. And we can also establish some kind of CLT for them. I mean, they are asymptotically normal, and these were done by Abadi and Indens in their 2006 paper. In fact, this is the paper where a lot of the large sample properties were discussed. Prior to that, people used matching, but they didn't know about any of the large sample properties. And okay, so as I said, the first two terms, they are well behaved. They are of order this, and they are asymptotically normal. But as you might have guessed, that the last term, that is the conditional bias, that is not always of the order of n to the power minus half. And this is where all the trouble begins. Sorry, this is where all the trouble began, and we can of course say that tau hat is not root n consistent in general because of this conditional bias term. And even more surprisingly, the stochastic order of this conditional bias that increase with the number of continuous covariates. I mean, the dimension of the covariates x. If we will see a theorem regarding this that will make this precise. And all these were established in the paper by Abadi and Indens. And in fact, most of the large sample properties I'll be discussing now, they are from that paper. Or some other paper of Abadi and Indens. They did a lot of work in this area. Okay, let us now discuss similar decomposition for the counterpart on the treated population. So the decomposition is similar, exactly similar. Recall that earlier we had here 1 by n, and the sum was over the whole population, but here we are averaging over the treatment group only. And we have the term the second term ENT, and finally the bias term, which looks something like this. And in fact, we can slightly simplify it, and that makes it more intuitive, which is this. Okay, so you can see this is a bias and we are averaging it. So ultimately this whole thing is conditioned upon the x's. So this is the conditional bias, and then we have to take expectation to get the unconditional bias. And for tau hat t also, this bias is something which is not well behaved. Okay, so next let us discuss some theorems, important theorems on the large sample properties. And they actually depend on many assumptions. So I will read out the assumptions one by one. The first assumption is a more modest one. It is that it is on the support. What should be the support of X? The support of X, we assume that it is a compact and convex support, compact and convex subset of RK. And then the next part that may not be that may seem to be something which is not very modest, because we are assuming that it has a density first of all, and the density is bounded and bounded away from zero. Now bounded away from zero, that is not usually held, right? For example, for the normal distribution, the density is not bounded away from zero. But I think there is some procedure where you can, even if it doesn't have a density, you can consider a version of the density is bounded away from zero. So they just make this assumption. And the second assumption comes like this. It is about the unconfoundedness, and unconfoundedness is omnipresent. It is present almost in every paper on this. And there is another assumption on overlap. And note that what does this say? This says that given a covariate value, the probability that it will be assigned to treatment group that is neither very close to zero, not very close to one. And this is so the two what I should say, the two spaces should have some overlaps. Otherwise, we cannot estimate. We cannot estimate the differences. And we assume that the observations are IID from a common distribution of this. So these are the assumptions that are needed for tau hat, that is for estimation of ATE, average treatment effect. For estimation of average treatment effect on the treated, we need to modify. We need to relax some of. We can relax some of this, but we need some more assumptions that are in the next slide. For example, the assumption 2 is relaxed to be this. Earlier, we were requiring both y0 and y1 to be independent. Here, we require only y0, and overlap also is on one side. Similarly, similarly, the assumption A3 is also modified. And there is one more assumption which is very strong, I should say, and it says that the treatment group is much smaller than the control group. The control group is like of the power of you see, n0 is the size of the control group, and it should be like the power, the n1 to the power r, okay, for some r greater than or equal to 1. So these assumptions will be required for estimation of average treatment effect on the treated. Okay. So now here are some theorems. They are from Aditya in Ben's paper, 2006 paper, and they first state what should be the order of the bias. As you can see, under assumptions of A1 through A3, and there is one more assumption they are making. They are assuming that the mean functions, they are ellipses, and this assumption just makes the proof simpler, I think. And so they are saying that the conditional bias is of the order of n to the power -1 by k. And this is what I was saying in the beginning, that the stochastic order of Bn that increase with k. Okay. And they also show that the unconditional bias is not in general lower than n to the power -2 by k. And for this is for ATE, and for ATE on the treated, we have this result, and you can see here the exponent is more, it is n to the power -r by k. And here also we assume some sort of Lipschitz assumption. Okay, so these give the order of the bias. And okay, so next let us talk about consistency. Consistency is also similar. That is done in the similar assumptions A1 through A3, and assuming leaf-siege of both the mean function and the variance functions. And this is for the ATE, and the next one is for ATE on the treated. And I should say that even though we are happy with the assumptions A1 through A3 or these three assumptions, but the assumption A4, that is slightly problematic, because we are requiring the control group to be much larger than the treatment group. And in fact, Abadi and Inman state that what is done usually in practice, people tend to ignore the bias. Okay, often when they are using matching estimators to estimate the average treatment effect on the treated. And then Abadi and Inman state that, well, it is justified because in many cases the treatment group is much smaller because the drug can be expensive and others, the disease can be rare and whatever. But and they also say that when it is justified, as you just saw that this quantity, it is of the order of n to the power minus r by k. So if you forcefully assume that your r is sufficiently large, so you are assuming on one hand that n naught, the size of the control group, is larger than n1 power r, and then you are assuming that r is greater than k by 2. Under these two assumptions, you can say that, well, it will be of little of n to the power minus half, and then it will be dominated by the other two terms, and then the standard procedures will apply, right? And there is another regime there you are doing the matching using only one continuously distributed variable, and so there you are directly assuming that r is 1, and there also we have the conditional bias term to be of this order, and then we can say that the matching estimators are root and consistent. So these are some cases where you can ignore the bias because the matching estimators becomes root and consistent and the bias becomes little of 1 by root n. Okay. And okay, next, finally, let us talk about the asymptotic normality. So as I said, it is very hard to control the bias. So what Abadi and Invens did, they presented an adjusted CLT, an adjusted asymptotic normality. This just subtracted the bias, and they considered these two quantities. And obviously, if you just subtract the bias, then the rest two, they are well behaved, and you can apply standard methods, and then you can of course get an asymptotic normality. And of course, as a corollary, you can also get the asymptotic normality without the bias in the other two cases that I talked about in the last slide, that for ATE when k equal to 1, and for ATET when r is sufficiently large, r is greater than k by 2, and n naught is greater than n1 power r. So the general results are absent in these regimes, and there is a more recent paper by Abadi and Invens that gives asymptotic normality for the treated case when matching is done. Okay, I should have mentioned here, when matching is done without replacement. They, in their 2012 paper, they considered that case when matching is done without replacement, and they considered some more assumptions. Under that, they prove an asymptotic normality for this estimator on the treated. Okay, and what else do we have? Okay, lastly, we have to estimate the variance, because giving only asymptotic normality is not enough. We should know how to estimate the variance in order to get confidence intervals. But estimation of variance seems to be a harder problem in this area, and one estimator which was earlier used very often is that the bootstrap estimator. But Abadi and Invens showed in their 2008 paper that the general bootstrap procedure is not valid, in the sense that it is not consistent, even in the simple case when we have a single continuous covariate. So even in the simple case where we have root n consistency, where we have asymptotic normality, and where the estimator is asymptotically unbiased, even in that case, the standard bootstrap procedure fails to hold. However, their 2006 paper actually gives an ad hoc estimator for estimating the limiting variance, the asymptotic variance. And there are some other approaches like modifications of the standard bootstrap, such as subsampling methods in Romano and Politis, their paper, 1994 paper. So these are some options for estimating the variance. And another thing is that if you have the problem on the treated only, then we can have another estimator, which is a very natural estimator actually. That is sigma hat square by n1, where sigma hat square looks something like this. As you can see, this is very intuitive, right? We are estimating tau hat t. Okay, sorry, here is another typo. It should be tau hat t. So tau hat t is simply the average of these quantities, and we can estimate their variance using this estimator. But surprisingly, even this intuitive estimator was proposed only in the 2012 paper of Abadi and Hindens, and that too for without replacement case. And for with replacement, this estimator actually fails. This is no longer consistent, and that was shown in the earlier paper. Okay. So I think that's all that I wanted to say now. I have a few more slides that is regarding another thing, actually, that is regarding their 2012, but I can briefly say what is that. So in their 2012 paper, Abadi and Indians, they derived a martingale decomposition for this adjusted estimator after subtracting the bias. This decomposition is same as earlier. They are just rewriting it in a new fashion. Okay. If you go to the earlier slides, you can see these and these, they are exactly same as what was there in the earlier decomposition. But what is new here is that they state this is a martingale representation because these are what? These are mean zero random variables, right? So if we just be a little more clever and if form the filtration cleverly, then we can form it, we can think of it as a martingale array, and then using the martingale, the CLT for martingale arrays, they established a result that is a CLT for the tau hat t. That is in the next slide. So I just I'm going quickly over this because I do not want to just describe it in details here. This thing is just a martingale array that you can remember, and so this is the final result. Again, you can see that they put a lot of assumptions, and under these assumptions, they finally derive a CLT for tau hat t, and this is not an adjusted one. Here they are killing the bias in a very clever manner, and which is not very, what I should say, very modest. They are imposing this assumption which is not held in usual practice. So in fact, I can tell you what they're actually assuming for this assumption. They are proving this assumption. Okay, here D is, recall this D is the sum of the discrepancies that we should minimize for matching without replacement. So they are saying that this should be little o p of square root of n1, and they are actually proving this under a much more stronger assumption that the treatment, again the treatment, if the size of the treatment group is n1, then they are assuming that the size of the control group is as large as n1 power k. Okay, so that is not usually held, I think, in practice. And so even though this theorem is interesting in theoretical manner, but the assumptions are very bad, I should say. This particular assumption, the Lipschitz assumption, there can be modified, but this assumption cannot be dropped here because without this assumption you cannot kill the bias. Okay, so that's all I wanted to talk about, and now you can ask questions. Any questions?
I don't think anyone has any more questions. Thank you, Aditya. Be sure to join us next week on a talk by Ritvik Chakravarti on unimodularity and geometry of random graphs. Thank you.
Okay, thank you, everyone. So I'm stopping sharing now. Yeah. Thank you.